Okay, science time. Today we are talking about, I think the objective reads, compare the forces of the universe. So let's label this forces of the universe. And so we're going to have both, we're going to describe what forces are in general, and we're also going to have some examples. So why don't you start out by, and you should know this from your explorations, why don't you start out by telling me, what is a force? Define force in some way. Okay, we can start with that. So we know it has something to do with motion, right? Has something to do with motion. Forces are somehow related to motion. I'm going to provide a counterexample. So Aiden said, partially correctly, that a force is something that makes it move. Is there a force acting on my keyboard right now? Let's actually like this. Is there a force acting on my marker right now? Yes. Let's diagram it. Okay, we're going to do. This is called a force diagram, and you should be able to do these. Force diagram. Here's my marker. This is not a good drawing of a marker, and I apologize for that, but I did my best. This is my marker. What forces are acting on the marker? Gravity. So what we do for a force diagram is we put a little dot at the center of mass. That's where we pretend all the mass is concentrated at a single point in space, which we call the center of mass. Center of mass. Why? Well, in real life, the mass is distributed all throughout this object. Yes, so far so good. But in physics, it's very convenient to pretend like it's all concentrated right here at this dot so that we can do easier math with it. And for another thing, it actually does behave that way. If I throw this marker, I'm going to close it first, but if I throw this marker, which is not allowed, you can't throw it, but I can. If I throw this marker at Mason, I'm going to put a little bit of spin on it, but you'll see. Now, wait, before he throws it back, watch as it spins. What point does it spin around? Like, what is its axis of spinning? Go ahead.
Center of mass.
Yeah, the center of mass. It spins around the center of mass. So there is other mass here, but it's behaving as if it's concentrated at the center point. When we throw it, it throws at this kind of arc, and even though the rest of the marker is wobbling, this arc is the path that the center of mass follows. So, the forces acting on the marker, as I just held it there, are gravity. F sub g, which we call gravity. F stands for, guess. Force. Sub g. If you were typing it, you would write it as a subscript, like that. A little subscript. What's the g probably stand for? The lowercase g. Lowercase g usually stands for gravity. And then, when the way I was holding it, what is providing this upward force? Because there is an upward force. I had it held like this. What's providing that upward force? The what of my hand, though? Okay, what force? I'm squeezing it so hard that it's holding up? No. I'm not holding it very hard. Okay, let me say it this way. Imagine if my hands were covered in olive oil or butter or grease or even spit. Would I be able to hold it as well? No. Why? Because what's actually holding this up? The force of, I'll give you a hint, it's lowercase f. Friction. Friction. It's the friction between my little fingertips and the marker that are holding it up. But my hand is squeezing it, so how is the force of friction acting up? The force of friction opposes motion. Let's write that down. So we have F sub g, gravity, pulls what? Pulls objects always down? Actually, that's how we define down, is which way objects are pulled. Good. Of? Of? The Earth. Only the Earth. Everything in the universe is pulled towards the Earth and only the Earth. No, that can't be right, can it? Pulls objects with mass toward. Does this have gravity? You say no. How come the Earth has gravity and this doesn't? It has to be a certain size and then it instantly has gravity. No. The truth is that it pulls objects with mass toward all other massive objects. So everything with mass in the universe is attracted to every other thing with mass in the universe. there's an obvious difference in degrees. You're right. This is pulled toward the Earth because the Earth is the biggest thing around, except your mom. Nice. No, listen, dog. I apologize for that. But the gravity pulls everything with mass towards everything else with mass. But the more mass it has, the more it pulls other objects. That's why, look, this has mass, does it not? And this has mass. But if I drop them both, they don't go together. They go towards the Earth because the Earth is bigger. The Earth has more mass. So in a way, you were right, Aiden. But it's not as if a thing, once it gets to a certain size, it has gravity. It's actually, the bigger it is, the more gravity it has. And if these were the only two things in the entire universe, eventually, over cosmological time, they would gravitationally attract to each other. But that's the force of gravity. So the force of gravity is pulling this, in the way we think of it normally, in our normal life, is that it's pulling it down towards the center of the Earth. But the Earth is held towards the sun with gravity too, right? So it's objects with mass. And gravity is so weak that we only notice it on extraordinarily large mass scales. Friction, though, F sub F, friction, what does this do? Friction, right? If I'm, you don't think about it this way normally, but if I walk, it's hard to walk when you say you're going to walk because I don't know what my arms are supposed to do, but you say you walk, what's actually happening is I am, with your muscles, what are you doing? Are you somehow like using your muscle power to float across the room? No, I'm actually pushing back. If I'm walking, I'm pushing down and back on the floor, and the friction with the floor is pushing forward on me. That's Newton's third law of motion. You remember that? Newton's third law of motion is that when I push on the floor down and back, the floor pushes on me forward and up, right? A way you can test this is if I were to kick off my shoes and I have my socky feet on, which have less friction, I slide around more easily, right? There's less friction. So friction is the force that opposes. What's another word like opposes? It's in the what direction of motion? Yeah. That opposes motion. That's a little bit of a simple interpretation of it, but it's a force that opposes motion or intended motion. How come Newton's first law tells us that if I put a force on this chair, it will go on forever in that direction? How come when I put a force on it, it doesn't do that? Because of friction, yeah. How come if I don't put a very strong force on, the chair doesn't move at all? That's called static friction. You can write that down. Static friction. Static friction holds objects still. It's not the only thing that holds objects still, but if the friction is stopping motion, that's called static friction. As opposed to sliding friction, which is where if I do put enough unbalanced force on this, now it slides, it makes that noise, and it slides. That's preventing further acceleration. So we know that forces relate to motion, but, back to my marker example, are there forces acting on this? Is it moving? No. So that can't be the whole truth, right? Forces it's not just forces called motion. Let's be more specific. What kind of forces cause motion? Well, what's true about these two forces? Do you see them? When I'm holding it there, they're opposite. They're in opposite direction, and I drew the arrows a specific length because they are these two forces acting on it. When it's just sitting here, gravity and friction are, we say, balanced. These two forces are balanced. Balanced forces. What if I let go? I have to catch because I don't want to ruin the tip. But what if I let go? I'm essentially getting rid of this force, right? I'm getting rid of the force of friction, and now are the forces balanced? No. They are unbalanced. So let's put it this way. Unbalanced forces cause what? Do they cause motion? Now check it out. If that's true, so first of all, at this point it is causing motion. It would cause it to fall. But now imagine in slow-mo, but now it's stopped again. So this unbalanced force, now when it hits the floor, now there's the force, the normal force of the floor is greater than gravity. And so that causes it to stop. So we can't just say unbalanced forces cause motion. They cause a... What's true of the motion in both cases? The motion has done what in both cases? Okay, I spelled it wrong, but you're right. Unbalanced forces cause a change in motion. So either speeding up or slowing down, or what's another way that motion can change? What's another way that motion can change? Things can speed up, right? That's a change in motion. Things can slow down. That slowing down is stopping. That's a change in motion. What else can they do? What? That wouldn't be a change in motion. I'm going to toss this at you again, Mason. This time, instead of throwing it back, volleyball bat it towards Cameron. Okay, good. Okay, so listen. If he hadn't applied an unbalanced force, it would have kept going, right? But he caused its what to change? What do you call that? The direction. Good. Unbalanced forces cause a change in motion, like speeding up, slowing down, or change in direction. And these things together, you'll remember from your explorations, we call what? What are all of these things called? These changes in motion. What do we call this? Acceleration. They're actually all called acceleration in physics. In our daily life, we usually just call speeding up acceleration. That's why the gas pedal is called the accelerator. But in physics, all of these are acceleration. We don't use the word decelerate in physics. That's a made-up word. That's not, well, I mean, all words are made up. But we don't use the word decelerate. These are all kinds of acceleration. You might even sometimes in a physics problem see Sandy decelerated from 65 miles an hour to 30 miles per hour. But that's still a kind of acceleration. Acceleration just means change in motion. So write that down. Acceleration means... Cameron, are you writing any of this down? Yeah. Good boy. Acceleration is a change in motion. Acceleration is a change in motion. And what is acceleration caused by? Forces. Oh, every force? No, only what kind of forces? No. How do the forces have to be? They must... No. Unbalanced. Only unbalanced forces cause motion. And how can you tell if forces are balanced? Well, here the classic example is, here's Joe, here's Streety. If Streety is pushing with 5, what's the unit we use for forces, by the way? Newtons. 5 newtons. And Joe is pushing with 5 newtons. Is this balanced or unbalanced? We add them together. They equal 0. That's balanced. But Joe wins the tug of war, and he's now pushing at 10 newtons. They now equal 5 newtons right. Let me make this line longer, right? We subtract them because they're in opposite directions. Now it's unbalanced. Okay. Do you have questions about any of this before you go? No. Oh, what is it? Joe's stronger.